Hey everyone, and welcome. Today we're going to break down a huge idea in math that's all about connection, the relation. It's the hidden machinery behind everything from your phone's contact list to complex data science. We're about to see exactly how it all works. So you have to wonder, right? How does a field like math, which is all about cold, hard logic, deal with something as fuzzy as a relationship? The answer, it turns out, is incredibly elegant. Math has a super precise way to define and work with pretty much any connection you can think of. When you get right down to it, a mathematical relation is just a fancy way of doing something we do instinctively every single day. We pair things up. We connect a student to their grade in a class or a person to their phone number. It's really all about creating these pairs from two different groups of things. Okay, so before we can zoom in and define one specific relationship, we first need to zoom out, way out. We have to build a kind of universe that contains every single possible pairing between our two groups. And the tool for that job is called the Cartesian product. I know, it sounds a little intimidating, but the idea is actually super simple. You take one set, let's call it A, and another set, B, and you just systematically create a brand new, bigger set that has every single possible ordered pair you can make. And that phrase, ordered pair, is absolutely crucial. It means the order you write them in really, really matters. Let's see this in action. It makes it so much clearer. So, say our first set, A, just has the numbers 1 and 2, and our second set, B, has the letters X and Y. To build the Cartesian product, we just go step by step. First, you take the number 1 and pair it with everything in B. That gives us 1x and 1y. Easy. Then you do the exact same thing with the number 2, which gives us 2x and 2y. And that's it. This new set of 4 pairs is our complete Cartesian product. It's every possible connection between A and B. Now, this brings up a really common question. Is doing A times B the same thing as doing B times A? And the answer is almost always a big nope. Just look at the pairs. In A times B, the first thing in the pair always comes from A. But in B times A, the first thing comes from B. Since a pair like 1, x is totally different from x, 1, you can see the big takeaway here. With Cartesian products, order is everything. Okay, so we've built our universe of every possible connection. But let's be honest, in the real world, we hardly ever care about all the possibilities. We care about the connections that actually mean something, the ones that follow a specific rule. And that is where the idea of a relation really shines. So just remember, this Cartesian product we made, it's our giant swimming pool of every single possibility. Now, let's figure out how we pick out only the connections that we actually care about. And here it is, the formal definition. A relation is just a subset of that giant pool of possibilities. That's it. We're not taking every pair anymore. We are being selective. We're picking out only the ones that fit a specific rule that matters to us. This quote just nails it. The rule is the secret sauce. That rule can be anything you could imagine. It could be, is the capital of, like in the pair of Paris, France. Or it could be, is less than, like in the pair 3, 7. It's this rule that gives the relation its meaning and separates the signal from all that noise. All right, now that we have a solid grip on what a relation is, we need to learn the lingo. There's some specific language we use to talk about the different parts of a relation, and getting this vocabulary down is essential for really describing what's going on. So there are 3 key terms we absolutely need to know. The domain, that's our set of all starting points, our inputs. The codomain is the whole universe of possible destinations, and then there's the range, which is the specific set of destinations that we actually end up at. Let's start with domain. It's really simple. It's just the set of all the first elements from the pairs in our relation. So if you have a pair A, B, then A is part of the domain. It's just all of your inputs, plain and simple. Next up is the codomain. The codomain is the entire second set, that whole set B we started with. Think of it as the complete map of every single place our inputs could have gone, whether they actually did or not. It's the whole target area. And that brings us to the range. The range is a subset of the codomain. It only includes the elements from set B that actually show up as the second element in one of our pairs. So if the codomain is the whole map of possibilities, the range is just the list of places we actually visited. It's our list of actual outcomes, our outputs. Okay, this next part is where things get, kind of mind-blowing. We know how to define a single relation, but have you ever stopped to wonder just how many unique relations could possibly exist between two sets? The answer is staggering. Let's figure it out. The logic here flows perfectly from what we've already learned. Since we defined a relation as just any subset of the Cartesian product, then the total number of possible relations has to be the total number of possible subsets you can make from that product. And we already know how big that Cartesian product is, right? If our first set, A, has m things in it, and our second set, B, has n things, then the total number of pairs in their Cartesian product is simply m multiplied by n. Which leads us straight to this powerful little formula. Now, the total number of subsets you can make from any set is just 2 raised to the power of how many items are in it. In our case, the set is the Cartesian product, and it has m times n elements. So the total number of possible relations is 2 to the power of m times n. And trust me, even with small sets, this number gets astronomically huge really, really fast. And all of this brings us to one final, really important thought. A relation can be any collection of pairs. It can be messy, it can be chaotic. But what if we add one more rule? What if we create a special type of relation where every single input, every single element in the domain is paired with exactly one output? Well, that very special, very neat and tidy type of relation has a name, and it happens to be one of the most important ideas in all of mathematics. It's called a function. Thanks for joining me on this one.